I want to show you something I've been working on for some time. That's confirm you can see my screen now. Can you see my screen?
Yes, sir.
Okay. Okay, great. What can you see on the screen? It's a blue
Okay,
screen, right?
welcome
Or a
back.
simulator or something like that. Okay, okay, great. Hold on, let me log in on my second device so that I can. All right. So this is I've been working on this for almost a year, and um, this is a simulator, and I'll quickly walk you around, and that's what we'll use to for today's lecture, right? So all the episodes or all the lectures we've had in the past, everything will come on this simulator, and then it will be easier to deliver this lecture. The paid training also will use this simulator for it, and I'll show you the features. It's a lot of work that went into this. So I mean, you have, of course, the the courses. So there is a process control and automation track. There is a power generation. There is a PLC simulator. And then some other courses are coming. VFD. I mean, we've done all the, we've just not deployed it online. So all the physics engine, the computations and everything is done, you know. So you will see shortly. And then you have just the independent simulator. So that has different scenarios loaded. So you can do tank control, pump interlock, logic plus timer. You can do temperature control, separator, and all of those, right? And then you have the dashboard, you have the team, you have the grading, and then you have the admin platform where you can onboard. So this meant for organizational training and individual training. So, okay, let me log out and then let me log in now. So that is the default page. So each of the tracks is divided into three. So you have the fundamental track. I mean, under the process control now and automation, you have the fundamentals, you have the intermediate, and then you have the advanced, right? Forget about all the topics under this, all of those will still change. We focused on the fundamentals for now, and you'll see how comprehensive the fundamental is shortly. So, like I said, so this is the fundamentals. Yeah. So under the fundamentals, process control and automation fundamentals, you have you have 10 modules, right? I mean, at the end of the module, it's a capstone, where you design your own loop. And you will see how we treated the control loop, right? And so this track, right? So this is the recommended path for engineer, Now, if you go to the track map, you see foundation. Everybody needs to know this, whether engineer or whoever. So 4 tracks for the foundation. Then you have the dynamics, you have the advanced techniques, right? And then you have the integration. So that's how the tracks are divided. And then, so your roles, right? So what is your role? I mean, if you want to determine your path, as a plant operator, you need to understand from M1 to M8, modules 1 to module 8. You need to have a very deep understanding of it. For instrumentation, M1 to M7, the control systems engineer, you need to understand the full track. And even for the plant manager, it's M1 to M4, which is just an overview, essentially the fundamentals, and then you can select your part. So I selected this, and then I said, so that's how the fundamentals work. I mean, the content is still going to be improved, but this is what we're going to use. So we'll probably start from M3, right? And then walk through M3, M4, I mean, up till when our time is up, right? So under the courses also, we have for the power generation, this is targeted at an organization. And then this might interest you. This is the PLC simulator, right? And so essentially, you can actually write your ladder logic on this simulator. I mean, it's still not as sophisticated as simulators around, but we're not trying to copy those simulators. What we're trying to do is to give the opportunity for experimentation so that you can try a lot of things, and then see what works, break it, and so on and so forth. So you have all of here now, you have scenarios. So for the beginner, you have lamp with push button, you have your motor start stop with C-lane logic. You have your timer on your timer or a delayed lamp. You have your tank fill for intermediate now. You have your heater. You have forward reverse motor interlock. You have conveyor belt, part counter and batch control, alarm annunciator, latch, silence and reset. You have compressor with permissive start logic. You have pump, bearing temperature trip. And then you have the troubleshooting track also, where you troubleshoot, okay, a compressor won't start. So let's look at that, for example. So this is a pre-built scenario, right? So a compressor won't start. And why will it not start? If you look at the rungs, the first thing you see at the top here, these are the permissives. These conditions must be okay. That is, this permissive must be okay before you can energize the output, right? So the oil must be okay, the temperature must be okay, and vibration must be okay. All of these three, right? This is the start button here. Excuse me. This is the start button here. This is the stop button. This is the fault reset. This is the compressor itself, and this is the fault alarm. All right. So, I mean, because this is a troubleshoot, scenario, if you start this, right, ideally, it should. So, if you look, so this is the watch table, right? Look at this start PB here. So, if I click on it, you can see it goes through, but the compressor won't start. And simply because this interlock is false. Sorry, this interlock is activated, right? So out of the three, so oil pressure, temperature, okay, yeah, oil pressure is not okay here, right? But temperature and vibration is okay. So the ideal thing is, because it's a simulator, if I click on this now, right? If I click on that and then I start this, okay, it's still not okay. So now I need to go to the watch table, right? And then look for, troubleshoot why this did not work. What's happening here, right? And then force it. So that's it. I mean, you troubleshoot. So if you look at this address, the tag, the type, the value, and then you force it here. So the oil okay, this is the oil okay, it's false, but temperature is true, vibration is true. So if I go here and I click on this, right, you can see that the oil pressure here goes on, it becomes true. And then if I start the compressor, so why is my compressor not working now? Uh, and if I start this, I force that. Okay. Oh, sorry. So I was doing all of this. I did not run the program. So let me go take this back. All right. So this is the run. So I need to run the program first. Right. So this is the PLC scan. Right. And then you can see the cycle. Right. Cycle time. Right. So this is the amount of scans it has done. So, I mean, starting all over, if you do this, you can see, look at rung 004. Right. If I release it, right. So if I now go and force this, force it to be true, you can see the permissive is now okay, right? Once the permissive is okay, I should be able to start my compressor, right? Then you can see all of those now. So my compressor is running now, it's working. So if I go to, let's say, maybe while the compressor is running, I force this to on this to false, right? You can see the fault alarm, the fault lamp comes on, right? And essentially, that's how the simulator work. So I can reset this back. And the good thing about this is that you can actually save the program. So if I reset, okay, if I run, yeah, if you run for some time and you make changes, um, so one first, um, start this, and then stuff. So you see, your work is being saved, right? So you can load it and refer to it later. And um, so if you reset, you can choose to update this program, right? So if you click on repair, right, you can choose to update the program, adjust it the way you want, move the branches, delete branches, and so on and so forth. So that's essentially, so that's the PLC simulator there. The other simulators here also. So if you look here now, so you have this pump interlock. I mean, it comes with its own. I mean, this is standalone simulator with its own brief tutorial. You'll go through all of those. You go through all of those, and then here you can start. So you see your pump flowing in. This is your process tank. You can see the level and the percent. So something just happened, an alarm occurred, right? This is your sensor, you know, and it's versatile such that you can actually inject faults, right? So if I say pump one, for example, and I want it to let it stop, I mean, just stay stuck, then I can inject the fault, you know, into the process. You see that pump will not run, right? And then you can analyze the effect and all of those things. And then it has so you can monitor the tank level trend. You can, I mean, check your alarm active. I mean, it doesn't have a trend, of course. Pump flow. You can monitor your pump running and all of those things. So you have that. You can stop it and you can reset. And then there are all of this here for the two-phase separator. You have that also, you know. So you have your PID. This is the PID for level, right, which is controlling the LCV, level control valve. There's a PID for pressure, controlling um this should be the PCV, not G. Then for the temperature, also PID for temperature, controlling the heater. Of course, you know the PID is I mean, this is essentially coming from the PLC, right? And then all these valves having influence on this process, right? And then you have all these sensors here, you know, monitoring the status of the process. And then you have your shutdown block that is monitoring all the conditions that ensures that you have a good shutdown or not. Yeah. So we're actually engineering this to be the perfect tutor, you know, so that personally you can go through a journey from zero to advanced, you know, on a simulator like this. And you know, I mean, of course, you cannot replace hands-on with a simulator. But the good thing about simulators like this is that you you can get as much as 80% competency, you know, such that when you land in the plant, it's it's a total, I mean, what you see in the plant will not be new to you, you know. And the simulator is fully customizable. So if we have the drawing of a plant, then we can model it on the simulator. That's how it's been engineered. All right. So let's get into, if you have any question, I'll take one or two, and then we get into the business of the day. Any question or comments? Just one or two. Okay. I'll assume there's not. So I'm not sure if that's a message or something in the chat box. Okay. All right. So we'll start with, I mean, we deal with, yeah, thank you. Thank you. So,
Good morning, sir.
yeah, good morning.
Yeah. Sorry, please. I want to know if there's going to be a record from this tutorial because I'm currently in another meeting and I really want to know what's going on here. So I just want to confirm if there's going to be a record after this meeting that I can go back to. Thank you, sir.
Okay, I assume it's presently being recorded.
Okay. All right. Thank you, sir.
All right, please confirm it's being recorded.
Yes, sir, it's being recorded.
Okay, thank you. All right. So, okay, I have been playing with this. So, but let's click on M3. Let's start from M3. All right, let's start from M3. Let's go to the concept. So, and the way it's structured is it just do an initial review of the previous module, right, before going into this. So a couple of questions from earlier modules before you continue. Let's keep the review, right? So let's keep the review. Now, the four components of every control loop, you know, every control loop from the simplest thermostats to a turbine governor controlling a 100 megawatts generator contains exactly 4 types of components. No more, no fewer, right? This module names them, explains their physical roles, and shows how their signals connect. I'm quite aware that there are more experienced people on the call, you know, because we did not take the census of who and who on the call. That's why I'm emphasizing on fundamentals. And my belief has been that if you get the fundamentals right, it's just like building the foundation of a house, right? Whatever you build on it will be very solid. I've spoken to many people, and there has been, and I've noticed confusion between the terms MV, EV, and SP, right? And as control systems people, whether instrument operators or whatever, you just don't have the option than understanding these parameters, because these are the things you'll be seeing in the control room. As a maintenance person, these are the language that you'll be using for troubleshooting, right, in the field, right? So the four core components of every control loop, you have the process. So the learning objective for this module is that you need to be able to name the four components of every control loop and their roles. Then you trace the correct signal flow, that is from SP to controller to actuator to process to sensor and to the controller, right? You explain what happens when any one link in the loop is broken, and then you build a complete working feedback loop in the builder exercise, all right? So the process, a water tank being filled and drained is a process. A heater warming a chemical vessel, a turbine spinning at target speed, a separator maintaining operating pressure, right? And the process obeys physics. The process has inertia, it has delay, and it has gain, right? Those are the physics behind a process. And that's why we call it a process. It is not static. You start with something and then you take it through some steps and arrive at something else. So that's why it's a process, right? And when we understand the concept of inertia, the concept of delay, the dead time, right? It helps us in both ways as maintenance people or as people that engineers the process, because you can easily understand what a transmitter should read or when it should read it, right? And then the gain. So if I use the term of chemistry now, catalyst, if you drop a catalyst in a chemical reaction, what a catalyst does is it speeds up the reaction, right? So what our controller does is, when you have an error, the controller acts to eliminate the error, right? So we need to understand the concept of gain. So you cannot force a process to change instantaneously. This is why control strategy matters, because there is inertia, there is delay, there is gain, right? That is why you need to that is why you need to carefully select your control strategy so that you'll be able to accommodate these three factors, which are the natural physics law, of the process. So a simulator like this also was built based on the understanding of the physics law, right, between parameters. So that's the process. Then we have the sensor, which is or the transmitter. The sensor measures the process variable. So that's our first term. The pressure it measures the process variable and then converts it to a usable signal. That's why we have our 4 to 20 milliamp, 0 to 10 volts, 1 to 5 volts, and so on and so forth, right? So the pressure does, and the sensor does that. So it converts physical quantity to electrical signal, right? Without measurements, there is no feedback. Without feedback, there is no closed loop. Right? So that is instrumentation for you. Right? And then the sensor is the eyes of the control system. A faulty sensor produces false measurements. And once the controller gets a false measurement, it's going to generate a false output or an incorrect output. So the controller responds to a lie. Right? Now, the controller receives the measurements, compares it to the set point, and calculates corrective action. So you have the controller will receive the measurement, compares it to the set point, and calculates a corrective action. So you have three components coming out of the controller. So one component going into the controller, which is the measurements coming from the sensor or transmitter. One component already pre-programmed in the controller, which is the SP, right? And then the corrective action that the controller is generating that is going to the actuator, which is what we call the MV, and we'll see that shortly. So we'll see error equals to SP minus PV, right? So the output, it's a function of the error history, and then the error rate of change. Who can tell me what this means? Or in popular terms, this function, what is this function? Yeah, okay, PID control. So that is just the PID function, right? The proportional, the integral, and the derivative. So the rate of change is your derivative, your history is the integral, and then this is your proportional, all right? So the PID algorithm is the most widely used controller type in industry, and the 90% of control loops in production plants. I was in an event last week, and I said that there is hardly any industry globally that does not implement this PID algorithm in one form or the other. There is none. As in any industry that does mass production, mass processing. Of course, our computers, is running so many PID processes. As in this device I'm using to make this presentation, your phone, your electronic devices. So it now baffles me that why are people scared of PID? Because of its mathematics. If it's so vital to I dare say our civilization, why are engineers, not casing a very deep understanding of this? And the funniest thing is, for those that did engineering, especially EE, electrical electronics in the university, this PID is one of the things that you were taught probably in 300 or 400 level, So it's a very, very important algorithm. So number 4, we have the actuator. The actuator executes the controller's command by changing energy or material flow into the process, right? So bear with me. All of this will still be improved. This is supposed to be a diagram, right? But it will be implemented, right? So actuators are the hands of the control system. They convert the controller's logical output into physical change, right? So this is the signal flow. So you have your set points. You enter the controller as a target. Then you have the controller calculates the output based on error. So what is the controller in this case? Can someone give me an example of a controller? Okay, a PLC, right? Is there any? Okay, a PLC. Now, a PLC is a controller. So when we say a PLC, are we referring to Allen Bradley or Siemens? So now I want to really want us to have this perspective. The controller, what is actually doing this calculation? So let's agree that the PLC is just an industrial computer, right? It's just like you have your app that you downloaded running on the phone. It is the app that is executing so your bank app, for example, it's residing in your phone. It is the bank app that is actually executing the logic of your bank transaction. Only that the app cannot work alone. It is being hosted by the phone. The phone can take many different apps, but when you want to do your banking transaction, you use your bank app running on the phone. The PLC is the hardware hosting the controller. Okay, don't let me confuse you. Let me not use controller. The PLC is the hardware hosting the algorithm that implements the control. So in this instance, we are talking about the PID algorithm. And it is the PID algorithm that calculates, it does this calculation. It calculates the output based on the error. And that's, as simple and probably obvious that might be, that's a very important concept, right? A very important concept you need to understand. So the actuator changes the physical process, and then the process responds and produces a new output. The sensor measures the output, then the signal returns to controller, closing the loop. So this circular information part is what makes it a feedback loop. Once you remove any one element, then the loop breaks open. So in the simulation we're going to do now, you will build the loop yourself, the 5 blocks, right? You'll see 5 blocks. You click and connect them, right? And then you pay attention to the direction. And then when all 5 connections are correct, the loop closes. Then you watch the system run. The correct loop stabilizes the process. A miswired loop drifts, right? And then we have the key terms, right? You have the key terms, the process, the sensor transmitter, the controller, the actuator, the signal flow, and so on and so forth. So we just handled the concept, right? So the walkthrough, right? So this is just a guided exploration, So in this walkthrough, we physically connect the components of a control loop in the correct order, So you need to identify the components. You need to connect the signal flow, right? Then you need to close the loop. Then you need to reflect on the structure, right? What happens if sensor to controller connection is missing? What happens if controller to actuator is disconnected, and so on and so forth? So the loop builder exercise is not just about clicking the right blocks. It's about internalizing that feedback. That feedback requires a complete unbroken information path. So those are the 5 blocks. So now, so if you click on this and then you click on this, you can see the XP to sensor is not a valid connection. Try again. You click on this, you click on this. It's still not a valid connection, right? So XP is supposed to go to where? You can type it. Tell me. So XP comes into the controller, yes, right? And then actuator goes to where? Actuator from actuator, what's the connection? What will be, so actuator is selected. What is the destination block? The process, correct, right? So, yeah. Then controller to what? Controller goes where? Okay, let's see. So controller to sensor is not a valid connection, right? So controller to actuator is a valid connection, right? Now, process to where? Process to sensor. Then sensor to where? Sensor to controller, right? So you can see the direction. And this again is important because it shows you how signal flows, right? Imagine you find yourself in a plant, right? And you have to troubleshoot a control loop. Before you can troubleshoot anything, you need to understand that thing clearly. If you hold your phone presently and it suddenly goes off, unconsciously you will begin to trouble. The question you ask yourself is, why? Why did my phone go off? And then you check, is it charged? Will it be power? That is the first thing you check. And then you verify. You plug in a charger and you still don't see a reaction. You say, okay, could it be that this charger is not working fine? You remove the charger, you plug it into something else, and it works. And then you know that the charger is fine. So the problem is with the phone. It is because of your fundamental understanding of the operations of the phone. That's why you can step through that troubleshooting process. And the same thing applies here. When you know how signal flows, of course, you know that SP, you are not actually wiring it. You are writing. You sit on your computer, you just type a value, and then it goes into the SP, right? But from your controller, you wire your controller, the cards, your analog output to your actuator, and then your actuator to the process to the sensor, and then the sensor delivers data back to the controller, and you have your process. So if we run the demo, right? So you can see here the PV minus SP, so once the PV reaches whatever, so it means that the closed loop is working, right? So that's essentially how it works. And then we continue. So the quiz, there is a 9-question quiz, but there is going to be a question bank, right? Of the target is to have at least 100 questions per concept. So on the loop here, you have 100, so that by the force of practice and diligence, you will know this thing like, the back of your, palm, right? So you're going to have thousands of questions on the platform down the line, right? So now let's quickly run through this question and then we'll go to the next module. We'll still have the time here. So what is the primary function of the sensor in a control loop? Quickly look and tell me. A, calculate the corrective action. B, measure the process variable and convert it to a signal the controller can use. C, physically change the material or energy flow into the process. D, store the set point value. B. Okay.
It's this.
Okay, great. So next question. Which of the following correctly describes the signal flow in a closed loop control system? I don't have to read, so you can tell me quick. Is it S? Is it A? Is it B, C, or D?
B.
Huh?
B.
D. Okay, I'll just follow you. Excellent. So the explanation is there. All right. The next question. In a water tank level control system, which component is the actuator? That is the final control element. A, B, C, or D?
D.
Okay, someone said A. Let me see. A is the wrong answer. The correct answer
It's
is
D.
D. Okay. So next one, the controller in a feedback loop directly changes the process variable. True or false?
False.
Ah, true or false? Okay, false. All right. Next question. Select all components that are examples of actuators. All components that are example. Okay, so tell me, is A an example of an actuator?
Yes.
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 Yes. A and D. A and D.
Hmm. Okay. All right. So, question 5. Select all components that are examples of actuator, final control elements. Okay, so tell me, A. Should I click on A?
A, C, and D. Yes. Yes. A?
Is B an actuator?
No.
Is C,
No.
C an actuator?
C. No. Yes. C is an actuator. No.
Okay.
C is an actuator. It's a variable frequency drive used to control a motor pump. So it's an actuator.
Yes, he's an
So,
actuator.
C,
so I
C
have
is an
the
actuator.
okay. So C. Okay, let me just click it. I mean, we'll see. Let me sort this. Okay. Okay. C. Then D.
D is an actuator. Yes, D is an actuator.
Yes.
D is an actuator.
Then E.
No.
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 Okay. So I can submit. All right. So we see that C is an actuator,
Variable
right?
frequency drive.
Because the signal, the controller outputs a signal to the drive, right? Even though, so probably the confusion came from the fact that the VFD can act on its own because the
It's a
VFD
controller.
can run a PID algorithm, right? But from the perspective of the control loop, where we have a controller, the sensor, and an actuator, right? The VFD is an actuator. If we don't have a PLC in the loop, the VFD becomes the controller.
The controller.
Do you understand? So you can begin to see the reason why we need not a memorized understanding of these concepts, but a deep fundamental understanding that we can think from the first principle and defend our answer that I because this and this and this, or because of this perspective. Yeah, let's move on. So in the loop builder exercise, what happens if the sensor to controller connection is missing? So if the sensor is not connected to the controller, what happens? Will the process runs faster but less accurately? The controller
No.
switches to manual mode automatically. The loop becomes open, no feedback, no correction. The set point is automatically recalculated from the process data.
C.
C.
C. Okay.
C.
Eh?
C.
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 Yes.
The answer is
Okay.
C.
You said B?
C.
C.
C is the answer.
Okay,
Okay.
C.
Feedback.
Okay.
Let's
So,
check C.
and this is the explanation. Without sensor, the controller never receives a PV. And without a PV, there is nothing the error can calculate.
Yes.
The error is what is the error? Is it SP minus PV or PV minus SP?
SP
SP
minus
minus
PV.
PV.
Okay. All right. So you won't be able to do that calculation without the PV. And it is a sensor or transmitter that supplies you the PV.
PV.
Right. Now, question 7. The brain of the control loop, the component that receives the measurements, compares it to the set point and calculates the corrective action is the what?
The controller.
Controller.
The controller,
Yeah, that's
D.
pretty obvious, yeah. Then a technician disconnects the sensor cable from the transmitter in a closed loop temperature system. The controller is still running. What symptoms will appear on the PV trend? Yeah, tell me. The technician disconnects the sensor cable from the transmitter in a closed loop temperature system. But the controller is still running. What symptoms will appear on the PV trend? I see A. Okay, A again. So let me pick A.
B.
So why is A not the answer? Okay, let's just read the explanation. So B, PV drifts away from SP. MV stays constant because the controller sees no signal. You know, MV is influenced by the relationship between PV and SP, right? So if you disconnect the sensor cable, what you are saying is SP minus 0, right? And then the controller will just generate MV accordingly, right? So without a sensor signal, the controller typically receives either a default value, a bad value, or a failure value, right? In most DCS implementations, a disconnected sensor causes the PV to display as a stale or erroneous reading. The controller, seeing a constant PV, calculates a constant error and holds the MV constant. You know, SP minus PV is always changing, right? On every scan of the PLC, SP minus PV is always changing. So if you look at the trend, it's not a straight line. But once PV is absent, once PV becomes 0, SP becomes a straight line. It's flat lines. The error flat lines, right? And then the controller will just generate an equivalent MV, you know, and then the process goes crazy. All right. So which single connection, if removed, converts a closed loop control system to open loop without removing any hardware? The power supply, the sensor output signal going to the controller input, the controller output signal
B.
going to the actuator. Eh?
B. B.
You've seen the clue, right? So once you remove that sensor, then there's no feedback. So you now have your open loop. So how do you convert feedback loop to open loop. Let's take out the sensor. Then you finish the quiz, and then you have your badge, right? And then, cohort average is 74, and then you have the summary. And the goal down the line is that, we're going to have, okay, I'll keep that information, But so the next one is process variables, right? So this is the next module, M4, right? So just drill down a bit into the variables so we can skip the review. We can skip the review. So the language of control engineers, module 3 give you the structure, the 4 physical components of any loop. Now we formalize the vocabulary. Precise language is not academic formality. It is how we engineers communicate across disciplines, plants, and countries. Wherever you go globally, this is the language we use. If you give any engineer any drawing, right, you don't even need to say anything to him again. Just deliver the drawing. He will have an understanding of the plant. You just have a few questions to clarify, especially when that drawing has been kept updated. So that's the engineering language. So the objective here is that you define PV, SP, and MV, and disturbance and error using precise engineering technology and terminology. You calculate error, right, as SP minus PV and predict controller direction from its sign, because this sign matters. This could be positive, it could be negative. You identify which variable the disturbance affects first in a closed loop system, and then you correctly answer both interactive identification prompts in the variable roles simulation. And then you have the coach. PV is the reality, what the process is doing. SP is intention, what process should do. So there's a difference, what the process is doing and what it should do. And then the controller never sees the disturbance directly. It only sees PV drifting from SP. So the controller only infers the state of the process from the PV that comes in, right? So it doesn't see the disturbance directly. MV is what the controller can change. PV is what it cannot change directly. So the controller can only change PV through MV. I hope it's not confusing. Okay. So watch the trend chart. When PV drops, error grows and MV rises to compensate. So, those are just So now process variable is the real measured value of what is being controlled. So tank level 42%, for example, temperature 73.6. Those are variables. Flow rate 12.4 meter cube per hour. Generator frequency 49.87. PV reflects reality. What the process is actually doing right now. It is what the sensor measures and transmits to the controller. So if you can't see it on a trend, it is a PV, right? Sorry, if you can see it on a trend, it is a PV, right? And then the set point is the desired value for the process variable. SP reflects intention, what the operator or engineer wants to do. The MV is a manipulated variable, right? Is a variable the controller changes to influence the process, right? So the inlet valve position, 65% open. This instruction comes from the controller. The heater power, 78%, supply 78% power to the process. The pump speed, 1,420 RPM. MV is what the controller can change. The controller cannot directly change the temperature in a vessel, but it can change the heater power, which changes the temperature. So the MV is the lever, right? It's the influencer. It's the MV that directly influences the process. PV is what you measure, MV is what you move. A disturbance is anything that affects the process variable, but it's not controlled, right? So downstream demand increases, increasing outflow from a tank. In some areas where their transformer is not does not have the sufficient power to carry the load, maybe in the early evening when people have not arrived at home, your light bulbs will be bright and shiny. But by 8, 9, 10, when the whole of the community has settled back in, you see the intensity of your light bulb drops, boom, right? Because there is more demand. So that is disturbance, right? Your electricity output is not maintaining the kind of, your bulb cannot stay at the level of illumination that you desire. As people switches on power in their house, the power drops and performance degrades. So disturbance creates error. They move PV away from SP. The controller cannot see the disturbance directly. It only sees the effects, right? PV deviating. And we have our error, which is the SP minus PV, and then putting everything together. So all of this, we've seen that. So disturbance increases flow. So you suddenly open the tank, in some houses where they have a pressure, like a pump and a pressure, I don't know what they call that thing. A booster, yeah, a pressure booster, right? If you open the water, at some point, you see the pressure booster will just automatically kick in, boom, right? And the purpose is to maintain the pressure, the water pressure coming out of the tank, right? So the PV drops below set point, the error becomes positive. Controller dictates positive error and increases its output. MV opens wider to increase flow. PV recovers towards SP as inflow exceeds outflow. And every loop follows this sequence, whether it controls a water tank, a nuclear reactor, coolant circuit, or a hydropower turbine governor. All right. So let's move on. So this is the walkthrough of the simulation that we'll look at now. All right. So observe variables in steady states, then the disturbance fires, then interactive identification challenges, and then so you will look at the challenge 1 at t equals to 160, which variable dropped because of the disturbance. And then at t equals to 170, which variable did the controller automatically adjust? And then recovery and reflection and summary. So you have that now. All right. So we looked at this earlier, right? The learning objective. So you watch how PV drops when the disturbance hits. Then the controller opens the valve MV. So this is essentially a tank application, right? You have this valve, right, allowing flow into this tank. So at this point, PV is SP, right? Am I still online? Can anybody hear me?
Yes, sir.
Yes,
Okay,
sir.
great. Thank you. So PV equals to SP, and then you have this outflow downstream So if you open this valve here, right, the water level will drop, meaning that PV will just drop, SP will remain the same, and then there will be an error, right? So these are variable monitor. The PV is 50%. The set point is 50%. So our process is presently at the desired place. The MV is presently opened at 50%. That is the valve position, right? Controller output. Now, the error is 0.0% because SP minus PV is 0, right? And then once we click on start, so this is T equals to 0 seconds, and disturbance will fire at T equals to 120 seconds. Programmed this in there, right? So let's start. So you can look at this. So the process is still behaving. So you can see PV is still 50, SP is still 50. All right. So you can see the disturbance has kicked in, right? So now, which variable changed because of the disturbance?
Tank level.
The tank level, which is the PV, right? So which variable did the controller automatically adjust in order to compensate for the disturbance?
NV.
MV,
NV.
correct. Right. So you can see that. So, I mean, MV just opened, right? And then in order to correct the disturbance, you can see that as MV opens, the error begins to reduce, right? And then SP remains constant in all of this. It doesn't care. It doesn't, whatever it is, it just stays there. It doesn't change. So PV changes, MV changes, error changes, and it continues like that. So both questions answered correctly. You can see PV recover towards SP as MV was adjusted. Okay. All right. So let's go to the next one. So we have our quiz. Let's quickly run through this quiz. And maybe we can look at the next module. So what does PV stands for? Process value, process variable, proportional value, pressure variable.
A. B. B.
B.
Oh, sorry. B. Sorry.
Yes, B.
Okay. In a tank level control loop, the set point is 50 and the current level PV is 43. What is the error signal? -7, +7.
Plus 7%.
+7.
Yes.
Let me click
Yes.
carefully. Oh.
Yes.
Okay.
Yes, +7.
Okay. Okay. So because error is always SP minus PV,
Yeah.
right? From the previous exercise, is it correct for the MV to be at 50 at T equals to 0 when SP equals to PV? Yes, it is correct. What are your thoughts, Emmanuel?
So I'm thinking that if we are if the sensor is sensing that the process variable is already at the set point, then why is the MV
At
open
50.
at 50%?
Okay, where do you think MV should be?
I think it should be at 0 since we are already at the target.
No, I
So
mean it's so not necessarily at 0. It is MV will be at the point where the controller, you know, what MV does is that it generates a signal that maintains the process in a stable state. So if 50% opening of the valve is what keeps that process, that keeps the error zero, then that's where it will be. I think I know where you're coming from. There is no output from the valve, right? I mean, from the
Yes.
tank, right? Because
Yes.
there's no. But in reality, the tank the valve at that output might be passing.
Okay.
What it means, what we mean by it passing is that there might be some leakage. There might be some leakage and it has to be maintained. Don't look at the value of the MV. The controller has calculated that keeping MV at 50% ensures that SP minus PV equals to 0.
Okay.
Do you understand? Yeah.
Yes, I know. Thank you, sir.
Okay. A pleasure. Okay. I'm not sure the answer is okay. Of the one we have on the screen. Okay, let me assume. Okay. So positive error means the tank is below target. The controller increases its output, right? And negative error, the opposite. In closed loop control, the controller directly measures and reacts to the disturbance affecting the process. True or false? Oh yeah, tell me. True. Okay. So it's false. This is the so in closed loop control, the controller directly measures. Does the controller measure?
No.
No.
And then
It receives
again,
signal
does
from
it
the sensor.
does it directly react to disturbance?
No.
No,
Exactly.
no, it
It
doesn't
only
directly.
influences the MV,
No.
right? The controller does not see the disturbance directly. It only sees the effect of the disturbance. And the effect of the disturbance is as PV deviates from SP. So it is using PV to measure the amount of deviation, right, caused by the disturbance. So the demand surge is invisible to the controller. The controller doesn't see, and even physically, the controller doesn't send anybody. It stays inside the cabinet in an air-conditioned room, and then the process is in the field. So it has servants carrying information to and fro. All right. This is both the elegance and inherent delay of feedback control, right? Select all examples of manipulated variable. So we're looking for manipulated variable. So A, is it a manipulated variable?
Yes. Yes.
B,
No.
C,
Yes.
Yes.
D,
No.
Yes.
Yes.
C is also part
E,
of it.
no, E, no.
Yes.
Okay, so we are not all agreed on D, but I'll click on
C
it.
and D.
Then
Yes.
E no.
C and
E,
E
no,
no.
okay. So we have A, C, and D.
D.
Let's see.
Yes.
So the pump speed set by the controller, right?
Yes, by the controller.
So in the simulation, a disturbance increases tank outflow suddenly. Which variable changes first as a direct result?
PV.
PV. The tank output.
Yes.
Okay. PV. Next question. The formula used by PID controller is
SP minus PV.
plus. Okay, minus. A tank level controller has SP45, PV52. What is the error and in which direction will the MV move?
Minus
I
B.
think
B.
B.
Yes.
okay.
After a disturbance causes PV to deviate from SP, which variable changes first and which follows after?
B.
B.
Oh no.
B. PV changes first.
Not D.
No, the answer is B.
B.
No.
It will deviate from F.
B.
B.
B. B.
Okay.
B.
All right. Okay. So we got 89%. We earned 40 experience points. And then you have your badge. And then the next thing. So feedback thinking. So it's 24. It's 24. Oh, apologies. So, yeah, I'm not sure we'll be able to finish this given the time remaining, right? But what this system is going to do is eventually I'm going to turn the 2 weeks tutorials into weekly. I mean, because I won't have the burden of having to prepare material before the tutorial. So down the line, I'm going to just choose 1 hour, right? Regular 1 hour every week. So I'll record the tutorial and just upload it. Anyone that's available at that time can join. And those that cannot join will see will find the recording. You know, it's because of the burden of having to prepare slides and stuff. That's okay. So that if we space it, we'll be able to, you know. So we'll be able to move faster now. I think, just walk through this maybe in 10 minutes and then we'll call it a day. If you have questions. Oh, no. So, but I don't want to rush this actually. You know, because this is the foundation of the proper process control. You know, so the control thinking, control is error correction over time. It is not instantaneous. And we need to understand that intuitively, right? So error is not a problem. It is information. And then correction is gradual. And correction is gradual because of the physics of, material physics, the physical processes. You supply it to a container now. It takes time for it to increase, for the temperature to increase or to get to a particular level. So there will be some delay, there will be some lag, right? And then overshoot when correction becomes excess, right? And all of this overshoot comes as a result of this lag and dead time, right? Then oscillation, energy imbalance. And then you now talk about stability, converge. It's stability is all about convergence and not, problem. So, real world. So the grid frequency is the PV. I mean, the grid must stay around 50 hertz. So when we say that, oh, we have what do we grid failure or whatever? What do we call that thing? When the grid goes down, what do you call that event?
Grid collapse.
Grid collapse. So whenever we have grid collapse, there is a wide deviation from this 50 hertz, right? So the governor, not a governor, not the political governor, but the governor is a controller, you know. So we put a hello. Can you hear me?
Yes, we can.
Man, I'm sorry. Hampton did me dirty. I had to change to a glow. I apologize. Right. Okay. I mean, they wasted so much time. Let me just share and conclude. Where's the sharing button again? So, okay. Share screen. Okay, so I mean, I wanted to do the walkthrough, but not sure if we have. I mean, and I don't want to rush through this because this confirm you can see my screen, please.
Yes, yes, you can.
Okay, okay. So I don't want to rush through. Excuse me. I don't want to rush through this because this is where we begin to talk about the various terms of the 1 second. Second, please. So this is where we begin to talk about the various terms of the the aggressive, the balanced, the conservative. But okay, maybe sorry, simulation. So let's look at the conservative. So you have your KP at 0.8 and KI at 0.02, right? And let's start. So you can see how slowly this is going up, right? Right. Look at how slowly it is increasing. That's the temperature, right? And you have your set point at 60. Right. Okay, let me. Okay, it's almost at set point. So you can see it's settling close to the set point, right? So there is no overshoot, right? And it gives a very clean response when you have a conservative PID setting. But you have to pay in terms of speed, right? And then, okay, let's go to aggressive from conservative, right? And then you look at it. So you can see the speed with which that is going, right? It's aggressively doing the compensation, and you can see what happens, right? It gets to, you can see the error minus SP, right? You can see all the overshoots there, right? So this aggressive whatever, it changes. I mean, it has energy implication, right? Because you use more energy in bringing the process back to stability. But I'll talk about it, patiently and in detail during the next class, right? So run complete. So you have your maximum overshoot plus 0.5 degrees, right? It's acceptable, right? And then look at balanced, right? And then let's start that. All right. So you have your maximum overshoots and acceptable, at 2 plus 2 degrees, and you have, I mean, it's acceptable, but again, it's your process that determines the nature of your process that determines what's acceptable or not. Imagine a process, let's say at an industrial scale now, people that have fried plantain before, you know that the plantain is looking, maybe, is it yellow now? And then you just blink your eyes and then everything starts going brown and dark. So meaning that the margin between that change of color is very narrow. So the overshoot that you can allow in that process has to be very, very small. So that's just to show that the process actually determines your acceptable overshoot, right? And then continue. Then we answer all those questions. So because we're still going to come back to this module 5, we'll not run through this, So so the last announcement I'll make today, we announced earlier, I think that the previous class, that there's going to be a paid course, right? And one of the reasons we delayed was so that we can get this back up into, we can quickly ramp up and get this ready for that paid course. There's no point having a paid course with running it with just PowerPoint slides, So, but this is okay now, right? So information on registration will be the curriculum itself. So we have the curriculum here, right? Forget about this price here, right? So we have the curriculum here, but the detailed leaflets will be shared during maybe by Monday or Tuesday. So you have the intro to industrial automation, you have your sensors and transmitters, and we'll look at all of this. You have the control valves, we'll talk about the CV, right? The trim types, the bench set, the positioner, and fail safe, what all those concepts means. We'll look at PLC programming, right? This is essentially introduction. So it's not intermediate, right? Introduction is you don't have any knowledge of the PLC. So we'll be looking at the hardware, looking at the organization, how the PLC itself is organized. We'll look at some OEM PLCs as case studies, Schneider, Allen Bradley, and Siemens. Right. We'll understand what the standard is, right? Ladder logic is part of the standard, what we'll program in ladder logic, we'll write some program, and then we'll look at what contacts, coils, and timers, and even counters. We'll look at all of those. We'll look at SCADA and HMI, and then we'll have an understanding, a very high level understanding of safety and standards, and there will be a capstone. So this is going to run for 6 weeks, right? And information will be, the leaflet, everything is ready. So registration information will be given. So for now, this is the only thing that is locked on this, on the on this simulator. So this is going to be where that training will take place. The modality will be shared, right? But if you're not ready to work, I mean, this is real work. There will be assignments, there will be reading materials and all of those things. So the number of hours you need to devote and all of those things will be communicated early in this new week. So I think that's the final information I want to give. If you have any question, you can ask me. Yeah, definitely there will be a certificate of completion. Yeah, definitely. There'll be a certificate of completion. Yeah, any question? Yeah, Achan, yeah.
Yes, sir. Good morning, sir. Thank you very much for the class. We really enjoyed it, I personally. And every information you've given is well taken, sir. So we will be very enthusiastic this week to see, to carry out the tasks you have said about how we are going to go about the course and all that. So, sir, just quickly, based on the lecture you gave today, I just want to confirm whether I am right with my observation about this controller and PLC. I jotted something down.
Okay.
Yeah, you said the sensor supplies the PV, if I'm correct.
Yeah, the sensor is the source of the PV. Yeah.
It's the source of the PV. So from my understanding, that means the PLC is also the source of the SP, the set point.
So the source of the the operator, the human operator supplies the SP to the PLC. So
Okay.
so if you say that the controller supplies the SP, you are right. But the source of the SP is actually from the human operator that types in that SP physically into the either physically or programmatically into the PLC.
Yes, okay. So I can say PLC, which is the controller, supplies the set points, while the operator is the source of the information into the PLC.
Okay, yeah.
Okay, and lastly, sir, you were explaining and giving a comparison between a bank app and PLC, and you said something that the PLC is the hardware hosting the PID algorithm. Is that how you put it, sir? I was trying to write it down while you were.
Yes.
No.
Yeah. The control algorithm, right? So there are different control algorithms. PID is the most common, right? I mean, when we say algorithm, algorithm is essentially a maths formula.
Yes, sir.
Right. So we have you have the PID, you have your MPC, right? You have your advanced control algorithms, you have your cascade, so again, so all of these other algorithms you are mentioning, all of them, in fact, all 100% of them were built on this PID, meaning that essentially they are modifications of the PID algorithm.
Okay, sir. All right, sir. Thank you very much, sir.
Okay, my pleasure. Any other question? Any other question? All right. So if there are no other questions, then we will adjourn and continue our discussion if any on the WhatsApp group. So if you're not on the WhatsApp group, it's good you get there. And we're going to make the community a bit more lively in the coming weeks, right? So that it becomes like a database of knowledge where we can, share and analyze, brainstorm, argue, discuss, and then learn together and grow together. So thank you very much for your time and your patience with my internet. Right. And the recording will be posted on the YouTube link and shared in the group. So there will be no slide to be sent because I didn't use any slide. All right. Okay. So have a wonderful weekend, guys.
Good, sister. Thank you, sir.
Oh, bye.
Thanks, sir. God bless you real good.
Amen. Amen, Pastor. Mm.